All right, we are here this evening with Dr. Brent Carter. He is a space weather research scientist. He has his BS in physics from La Trobe University in Melbourne, and his PhD from the Department of Physics, also from La Trobe University in Melbourne, Australia, in 2001. He is currently a visiting research scholar at Boston College. And he is now currently back in Melbourne at the Royal Melbourne Institute of Technology, RMIT. The current time there is what, 8:30 in the morning?
Yep, that's right.
About 8:30 in the morning. So we're very appreciative of him taking time out of his day to give us a seminar from the other side of the planet, which is pretty cool. I want to make sure that we acknowledge the supporters for our seminar series. The UCA Foundation is thankful. We're thankful for the UCA Foundation for supporting our seminar series, and I'd like to have Dr. Carter take it away.
Great. All right, howdy guys. I'll bring up my slides and share it with you. What do we got? Okay. So my seminar is on, where is it? Wait for it. There it is. Space weather and its impact on our technology-dependent society. As I'm sure you are all aware, space weather is not a new thing. It's been around for quite some time. However, in the last couple of 100 years, our use of technology is drastically increased, and so the implications and effects of space weather on our way of life is becoming more and more important with time. What I've got here just on the title slide is a couple of pretty pictures. One from the ground on the left, taken from Tasmania. Of what the aurora looks like, which is typically, I guess, the textbook picture of space weather and what it is and how it affects us. But it's actually a lot more complicated than that. And on the right, we also have images of aurora from above from the International Space Station, about 300 or 400 kilometers altitude. So I thought I'd at least start with those pretty pictures. Now, what I'll do, I'll start with an introduction to the near-Earth space environment itself, and then discuss the effects of space weather on various technologies. Space weather is normally associated with extreme space weather events, like you would have heard from Dr. Halford about the Carrington event. We'll discuss that as well. Now we do have these extreme events, but we also do have day-to-day variability in the space, in the near-Earth space environment, which does affect us. As we go through time, we're having to consider the fact that that this is actually a thing we need to be looking at on a daily basis. So I'll give a brief history of extreme space weather events. I've got a. Oh, sorry, go on. No, okay. So we've got some an overview of some previous events, some very severe events, and then we'll have a quick look at how often do these events occur. And then we'll finish up with a recent solar eruption in July of 2012, and we'll discuss how lucky we were and what the potential societal and economic impacts of such an event would have been in this century. And then we'll finish with summary and conclusions. So the first impact of space weather on human technology that's been found was published in the journal Nature, as shown here on the left, where it was quoted that a train was made 16 minutes late because of the effects of space weather on the telegraph infrastructure at the time. This dates all the way back to 1841. So even though I guess for some cities, especially Melbourne in particular, a 16-minute late train is actually not bad. But I guess back then it was serious enough for someone to actually note in the journal Nature. So this is the earliest recorded impact of space weather on technology. Now, the near-Earth space environment itself, as Dr. Halford has already shown, mainly consists of four regions, or four parts. The sun, the solar wind, the Earth's magnetosphere, and the Earth's ionosphere. And my research in particular is focused on the Earth's ionosphere, but as I'm sure Alexa would have said, we basically need to consider everything that's going on in the near-Earth space environment, and we also need to be talking to each other a lot about what we're learning about our specific regions in the near-Earth space environment. Now, the typical extreme space weather event scenario is what's used well, in the popular media. And this normally consists of a coronal mass ejection leaping off the sun's surface out into space, along with the solar wind that's already being propagated outwards. And the problem is these things can tend to hit Earth or be Earth directed. And when they do, our magnetosphere acts as a little bit of a shield, but it doesn't completely protect us from the disturbance as it hits our region. So through various complicated phenomena, solar wind plasma eventually finds its way into what's called the cusp regions in the high latitudes there, and you'll see the plasma streaming in there, and that's essentially what your aurora is. And the aurora borealis or the australis is known for affecting both pipeline erosion and power grids. And a famous event where this was a big problem was in Montreal in Canada in 1989, where the power grid was actually knocked out of action for several hours, leaving millions without power. In addition to that, the ionosphere is also a natural reflector of radio waves. And so if we're using satellite communications or even ground-to-ground communications over the horizon, the ionosphere plays an important role. And this includes GPS signals, which are utilized by not only your sat navs in your cars and your phones, but also by agriculture industry and maritime aviation. And what was the one previous to that? I can't remember it, but essentially it affects everything that uses GPS. Now, the environment itself is the Van Allen belts in particular, which is what Dr. Halford was reviewing a couple of months ago, is quite a dangerous environment for the satellites themselves because of high radiation and surface charging that goes on. And we've also got to remember we've got people up there as well, which people tend to forget. Now, at the moment, we've got an array of of nice instruments and satellites and spacecraft in space that monitor the sun for us in various wavelengths, and we get to be able to use these in order to predict out any potential disturbances. So this is a schematic of what the near-Earth space environment looks like, minus the magnetosphere. So this is mostly focused on the ionosphere, and you can see how complicated it is. We have the sun, which is out in the distance. This obviously isn't to scale, but out in the distance we have the solar wind, and we also have the electromagnetic radiation that hits the day side and ionizes the upper atmosphere, which creates the ionosphere in the first place. In addition to that, the high latitude regions, we have a complicated plasma flow region that directly ties up to the solar wind through the magnetosphere, and this creates heating up in this region, and through various momentum and energy transfers creates changes in winds. We also have complicated plasma flow structures on the day side, so that there's lots going on. But one thing I did want to point out was this region here. This is in the dusk sector, so just after sunset we have these irregularities / bubbles highlighted by the diagram here. And these are a regular occurrence on a daily basis. And this is actually part of my specific research, but we'll get to that eventually. So this is quiet time. Now, when we add a geomagnetic disturbance, you'll see that we still have all that complicated structures and current systems and plasma flows. But now we've got additional gravity waves coming from the high latitude region, and we've also got an increased amount of energy going into the high latitude region, so the high latitude region becomes hotter. In addition to that, you also have changes in molecular composition at the changes in composition in the upper atmosphere, which give rise to all sorts of other various things as well. But you'll notice as well that these irregularities or bubbles here are still there. So we've got these phenomena that happen with or without storms. But ultimately, look, don't try and understand everything that's here. This is ultimately quite complicated, and we're all still trying to get our head around what goes on up there. Now, perhaps the most serious aspect of space weather that influences our technology is the effect of, so this should be geomagnetically induced currents that are caused by strong deviations in the local magnetic field strength. So this is essentially Faraday's law, where you have a changing magnetic field, and this generates an electric field in the Earth's crust. And you can see that with these current systems up in the high latitude region over top of Canada, these are going to give rise to quite a few or changing magnetic fields, which are going to influence the ground essentially. This also happens in the southern hemisphere, but you'll notice that around the auroral region, we're lucky enough to have that mostly covered by either Antarctica or the ocean. However, there has been recent research showing that we are getting significant geomagnetically induced current levels being observed in Tasmania, which is just the southern part of Australia here, and we're getting that's what these dots are here on the declining solar cycle phase here. So we're seeing that these events are still reaching latitudes that we thought were relatively immune to such disturbances in the past. The other thing that's important for us to know is that the ionospheric plasma, so this is the upper atmosphere, actually acts as it's a dispersive medium. So what this means is that if you throw at it a barrage of electromagnetic radiation, especially in the radio wavelengths, the plasma actually slows down the electromagnetic wave, and the rate at which it slows it down is dependent on the frequency. Now, a perfect example of this is an example that Alexa showed you last time, where you have a lightning strike on the ground, and the electromagnetic pulse that comes from that lightning strike actually travels up into space along the magnetic field line and then goes to the other hemisphere, and sometimes can keep bouncing back and forth. And the result of this is, I'm showing down here a spectrograph where you have a broadband crack, which is the actual thunder strike. And then as you keep listening, you'll hear that the high frequency waves actually arrive first, and the lower frequency waves arrive later on. And I'll just play that for you. Let me know if you can't hear this properly. So each crack in there is a lightning strike, and what sounds like the birds chirping is this dispersion that's taking place. How did that sound on your end?
Play it again.
Play it again? Oh, I've got two here. I'll play the second one, which is a bit nicer.
Okay.
And I'll play the top one more time.
So, Brent,
So
are
the idea
those multiple strikes that you
yeah,
can hear the whistle from one lightning bolt going through the dispersive media, or are those
that's right.
returned back and forth?
Well, they sometimes do bounce back and forth, but you'll hear in the top one in particular, there's multiple lightning strikes. So every single time you hear a significant crack or crackle, what sounds like distortion, that's the actual lightning strike, and the choo is the reflection of that from the other hemisphere. So as I said, if you've got your radio receiver here, you hear the crack of the lightning here, and that goes all the way to the other hemisphere and then comes back again. And along this entire path, it's encountering plasma, and so the high frequency waves end up traveling. Well, they travel faster in the throughout the plasma, so they end up arriving first, and then this gets followed by the lower frequency ones.
Cool. Okay. Thanks.
Cool. Now, so the plot up in the top right-hand corner here is a demonstration of how dynamic the ionosphere can be from hour to hour. You'll see that you do have this bright region that travels along the magnetic equator. This is essentially the day side, and you'll see that at the nighttime, even though you do have less plasma there, it still is spatially and temporally variable. So the point is, if you're needing to pass radio waves through this medium, you need to know how much plasma was there, or how many electrons essentially the radio wave passed on its way, so that you know how inaccurate, essentially when the radio wave left the transmitter and made it to your receiver. But this dispersive medium actually enables HF radio communications that that bounce off the ionosphere. Because it's essentially a natural reflector, you can use a HF radio transmitter and speak to someone on the other side of the world, which otherwise you would have needed a satellite relay for. So in this sense, it's actually quite handy for HF radio communications. But in addition to that, the Australian Air Force in particular, and I'm sure many others around the world, use HF radar surveillance to monitor their borders. So instead of having a whole heap of infrastructure lining the coast, for example, you're able to use limited infrastructure and have quite a large field of view because of the reflective properties of the ionosphere. So one important one is the global navigation satellite systems like GPS. The GPS satellites actually transmit multiple frequencies, but aviation, just like your sat-nav systems, they only listen to one frequency. And the problem is, if you've only got one frequency, it is slowed down by the ionospheric plasma, and you don't know how much it has been slowed down by the plasma because you don't know how many electrons were in the ionosphere. And as an example here, I've got on a plot on the lower right-hand corner of this is essentially showing the delay of the GPS signal as a function of time. And you can see that the delay changes substantially. I really should have a color bar here for the scale. But you can see that there are substantial gradients in here. And so depending on where you are and what time of day it is, your signal is slowed down more or less. Now, what the United States has, and there are similar systems in Japan and Europe, and I think there's a new one coming up in India. It's probably already operational, but you have what's called a wide area augmentation system, where you have a network of ground-based GPS receivers on the ground that listen to multiple frequencies emitted from the GPS satellites, and they directly measure how much ionospheric plasma is between them and the GPS satellite, and then they transmit all this information to one ground station. This rebroadcasts this message up to a satellite in geostationary orbit, and then this geostationary satellite rebroadcasts this message, so that this plane here, for example, actually gets correction information given to it by the satellite up here, telling it how much ionosphere there is above its location, and this can be substantial. Your positioning errors could be up to tens of meters, which is obviously not good enough for precision guided landings. So this is obviously an important aspect of space weather that does affect people on a daily basis. Now, these bubbles that I pointed out earlier in this other plot in the equatorial region are a significant problem for satellite communications and for GPS positioning. This is essentially an equatorial slice of the ionospheric plasma, with altitude on the y-axis and east-west in basically hundreds of kilometers. And you see what looks like these tree root shaped structures that after the ionosphere rises after sunset, the bottom side of the ionosphere becomes unstable, and then you have some nonlinear growth take place. And what happens? This creates very large gradients in the local ionospheric plasma. And if your GPS link happens to intersect with one of these bubbles, you have the potential of losing lock with that satellite. So instead of having 5 or 6 or even 8 satellites or data from 8 satellites to calculate your position, you actually have a reduced number as a result of these disturbances. And here's an example, a real-world example actually of scintillation. This is above Vanimo, which is in this region just north of Australia. And what I'm showing here are the satellite locations as a function of time. And when you see the asterisk that represents the satellite location fluctuating, you see this one flashing right here. This is it losing lock and gaining lock again. And when they're brightly colored, they're actually experiencing a lot of scintillation. And so precise positioning capabilities start to decline because the signal is less reliable than what it would have been. And you'll notice that there was one case here, or one period of time throughout this animation, where all of the satellites were actually experiencing significant scintillation levels. So this is an obvious problem for, again, anything using GPS. Now, one other aspect of space weather that's important is the amount of satellite drag experienced by the low Earth orbiting satellites. I remember being quite surprised to learn that we're not very good at predicting the orbits of objects in the near Earth orbiting environment, which is approximately about 800 kilometers. There's a very large range there, but there's a lot of satellites that we have at that altitude range. And the reason we can't predict it is for many reasons, but the main one is satellite drag. The top right plot here is showing a simulation of the neutral temperature, or the temperature of the neutral atmosphere up in the ionosphere. And you'll see towards the end of the simulation, we actually have a geomagnetic storm start. And so, as I mentioned before, you have increased temperature or increased energy input into the high latitude region, and this very quickly spreads. Now, as a result of the increased temperature, you actually have adiabatic expansion of the thermosphere, or the neutral atmosphere, as it's probably known by you guys. And this ultimately results in a higher level of satellite drag. Now, one particular case that was reported is going back to this 1989 event that resulted in this power outage in Quebec. We actually had, it's been released that the number of lost satellites by NORAD typically fluctuates between around this time anyway, fluctuated between 200 and 300 satellites at one time that they didn't know where they were. And then this yellow spike here indicates this very large geomagnetic storm that took place. And you see that the number of objects they lost went all the way up to about 1,500. And it took them several days, almost about a week, for them to find all of those objects that they lost. And in fact, one object in this event lost 30 kilometers altitude. And so obviously, as you guys know, with the conservation of angular momentum, their orbital dynamics completely change when you change the altitude of the orbit. And one interesting aspect of this, one reason why this is actually hugely important is because, as I mentioned, we try to predict the orbits of objects in order to avoid collisions. Now, this animation shows a real-life event where the Iridium satellite, or one Iridium satellite, collided with the Cosmos satellite. The calculated miss distance for this event was 50 meters. So you guys are physicists, so you know what a meter is. Essentially, they had quite a large error. They decided not to do any maneuvers or anything like this, and it resulted in a collision, which has now resulted in a huge increase in the number of debris objects that result from that collision. Now, such collisions increase the likelihood of many more collisions, not only collisions with other satellites, but also with each other. And each collision that takes place, they're increasing the number of objects that are up there. And so this is becoming an increasingly important problem. And of course, when we can't even predict out a week in advance where these satellites are going to be, this is a significant issue. And the fact that we have space weather controlling controlling the amount of drag being experienced by each of these objects, you can imagine that it's quite a serious issue. Now, one other aspect of space weather that affects us are radiation storms, or solar radiation storms as they're called, where we actually have high energy protons that get emitted from the sun, and they interact with our magnetosphere and then impact the high latitude regions. Now, what I'm showing here is the outputs of the nowcast of atmospheric ionospheric radiation, ionizing radiation system. And what this is demonstrating is that as you increase in altitude, or as your plane changes altitude, especially over the polar regions, your susceptibility, or how much radiation you experience drastically changes. So you see that 15 kilometers, where typically private jets and military aircraft will fly, you get quite a large dose, whereas as you go decreasing altitude, you can see that you can avoid quite a large amount of radiation. Importantly, we're showing the southern hemisphere now, but over top of the northern hemisphere, you'll see that there's a substantial part of Europe, the United States, Canada, that's encompassed by this high radiation environment. Now, you guys would remember the government shutdown that happened in the US in 2013. This system was actually shut off as a result of that government shutdown. And even though I think it's a pilot project, it's demonstrating quite useful capabilities in showing how much radiation aircraft are getting within the high latitude regions. Now, it's been estimated that during this event, there are approximately 500,000 people that were exposed, and it's also been estimated that 4 eventual fatalities may actually happen because of this event. But I should definitely note as well that there have been some other papers more recently that have critiqued the estimation of the eventual fatality number. And the problem is because it's a relatively low radiation dosage that you're getting up here. So it's equivalent to a few chest x-rays. But the point is, if you're flying and you're pregnant, then such information may you could use to delay your travel, like a pregnant mother would actually delay an x-ray because of the pregnancy. So it's a matter of managing the risk and making informed decisions based on your own personal perceptions. So this is obviously an important aspect, and these events don't actually have to happen for large geomagnetic events either. These can be sort of day-to-day things as well. Now, moving to a brief history of space weather, I'm going to start with the Carrington event because this is back in the 1850s. This is what has typically been used as sort of the doomsday type event. Now, obviously, at the time, we didn't have that much ground infrastructure, but we did have telegraph wires across North America and Europe, drastically impacted by this event. This map down here shows, the red dots shows the locations of aurora sightings, and as you've been seeing, most of the aurora happens up in the high latitude region here, whereas during this event, the more intense the storm is, the more equatorward the aurora becomes. And you can see as far south as Hawaii and Central America is where people were observing the aurora. And as Dr. Halford pointed out a few months ago, I think it was someone in either New York or New Jersey, a telegraph operator actually was burnt because the telephone wires all fried up inside the connection facility. So this was quite serious. And this is what this type of aurora looks like. It looks very, very like a blood red over top of the low latitude region. And so I guess this sort of thing for ancient civilizations would have been a sign that something dreadful was going to happen, even though it had nothing to do with what was going on. But nonetheless, an interesting event. Now the DST index, I want to introduce this. This is just a number that we assign. I mean, it does have some physical definition, but it ultimately tells us how severe the storm was. And because we didn't have many instruments at the time measuring this sort of thing, there's been estimations ranging between -800 and -1600, where the more negative this value is, the more severe the storm was. So I'll keep on directing you to these as we go through each one of these events. The next major event happened in 1921, where the estimated DST got down to -900. And this what was actually measured on the ground. If you remember me talking about the deviations in the magnetic field, I'll point out that this one was measured to be 5,000 nanotesla per minute. And so this is obviously going to result in quite excessive geomagnetically induced currents. And radio signals and telephone exchange disruptions were reported all over the world, including Europe, USA, and in addition to New Zealand and Australia. And there was also aurora once again observed in the Caribbean. I found it quite amusing to read that French telegraph operators said that their lines seemed possessed by evil spirits. And in addition to this, I trolled through some old Australian newspapers, and the Melbourne the Melbourne Argus, an old newspaper, actually reported that there were telegraph problems between Melbourne and Sydney and Melbourne and Brisbane, so up and down the east coast of Australia here. And I even checked the local paper near where I grew up, below a story about a guy that was being drunk and disorderly in the street and then finally getting arrested and getting fined £1 or spending 7 days in jail. There's actually a mention of this geomagnetic storm where a firefighter was confused to to see the what he thought was a reflection of a distant fire up in the sky. And then when he went up into the lookout, he couldn't actually see the fire. So this confused him. So there was a bit of a personal aspect of space weather back then, which we unfortunately seem to have lost a lot of. But I thought this was quite amusing. Now, the Quebec storm is another one that's a textbook example of the effects of space weather on us, or at least extreme space weather events. And this widespread outage that happened up in Quebec, shown on the left plot here, the magnetic field changes that caused this were only on the order of 480 nanotesla per minute, which, if you remember, is a tenth of what was observed back in 1921. So I just wanted to point that out. And yet we had power grid infrastructure completely collapse for hours. And I mentioned before that we had an increased number of lost satellites, and there was also a whole heap of other effects of this storm. And the photos here are of one of the transformers, sorry, that was essentially melted down and blown up as a result of this event. And I think, from my reading, I think these pictures of this transformer are actually from this one in New Jersey. Now, more recently, in 2003, we had what people have dubbed the Halloween storms. And this event only got down to negative 383 nanotesla, and this caused widespread problems all over Europe. There was flight reroutes because of the increased radiation levels in the high latitude region, and this cost airlines between $10,000 and $100,000 per flight in fuel costs. And in addition to that, there's been the failure of one satellite that's been attributed to this event, and that satellite cost several $100 million. The International Space Station astronauts were directed to take shelter. The wide area augmentation system that I introduced earlier, this had a vertical error that was more than 50 meters, which obviously meant that it couldn't be used for precision approaches anymore. And so this here is a map of where the wide area augmentation system is able to work, and this is what it looked like during the Halloween event. And of course, up here, this animation is showing the solar flare and the resulting coronal mass ejection that caused the problem in the first place. It was actually a couple of geomagnetic storms that happened in succession which caused all these problems. So it wasn't just the one event; it was two that one went right after the other. So that was quite a significant event. So putting all these events side by side, I wanted to just point out that. Or the DST, from what I'm dubbing the late train event, no one will ever know because we don't have we didn't have the infrastructure to measure it. But from this point onwards, we get an idea of, or at least from the storms I've picked out, it looks as if that the intensity of these storms may be decreasing, or at least of the more extreme ones. But at the same time, this isn't necessarily true, as we'll see. But on the right-hand side, where I've actually listed all of the technologies and people affected, you'll see that this is increasing and it's becoming more populated with time. Now, as I mentioned earlier, we had this event back in July in 2012, a very recent event. I'll first direct you to the bottom left plots where we have essentially a bird's eye view of the local solar system with the sun in the center, Earth sitting here on the right, and this plot's in the same format. You've also got the planets Mercury and Venus shown here as well. And in addition to that, we also have the stereo spacecraft, which have been on purpose put at Earth's orbit, but at ahead in Earth's orbit and behind. And these two satellites are actually merging toward, well, they're actually heading towards the other side of the sun now because they're slowly been transcending backwards. Now this event, you'll see your coronal mass ejection, or this is from this numerical simulation, this took up more, or approximately an entire quadrant of the ecliptical plane. And you'll see that the Stereo A spacecraft, which was here, copped the full brunt of it. Now this here is the coronagraph provided by that particular satellite. The white circle in here shows the size of the sun itself, and the black disk is just there to occult the bright sun so that you could actually see the solar wind pouring off the surface. And you see that it looks like a circle. The event or the explosion looks like a halo, and that's why it's been given the a halo type event. That's why it's been given that name. From the SOHO spacecraft, this spacecraft sits between the Earth and the Sun. It's about only 1% of the distance ahead of us, which in terms of typical solar wind speeds, it's about one hour upstream in the solar wind. And this is what the explosion looked like going out to the right from that orientation. Now, the scary thing is that that this event came from a region that was actually facing the Earth 1 week prior to it actually taking place. So in that sense, we actually were very close to experience, well, we're close not to experience this event. So using the data that we received from this satellite, some researchers have done some modeling showing that the DST was likely to be on the order of 500 nanotesla, which is, you know, among the most strongest within the last 100 years. But they've also found that using worst case scenario modeling, that this could have been more than doubled. And what worst case scenario means is essentially the time of year and time of day, because as the Earth rotates, the Earth's magnetic field rotates along with it, and so the orientation with respect to the solar wind plasma is varying as each hour passes. So they found that this event could definitely have been a Carrington-scale event, and it's only just happened a couple of years ago. So it was very significant. Even more scary about this storm is that we didn't have much time. Normally, these types of events take 2 to 3 days to propagate their way towards the Earth. This one got out to Earth's orbit in less than 19 hours. So on one hand, we've actually been lucky on several counts here. We were lucky that it missed us. We were also lucky that we had a satellite placed or a spacecraft located at the right place at the right time in order to completely measure everything about the solar wind, to perform some modeling and some research into what sort of effects we would expect down at Earth. So again, putting this on the end of our list of important events, you can see that the very bottom where we have our July 2012 event, that this is still on par with the more significant events in the last 100 or so years, or 100 or more years. And the scary thing is, as we're going with time, we're becoming more and more dependent on various technologies that are impacted more and more by space weather activity. And so even though we've taken a lot of comfort in the relatively low probability of such large events, we are nonetheless more vulnerable to them if and when they occur. Now, I didn't want to spend too much time on this, but I wanted to just mention that some researchers have tried to look at what the probability is of encountering such disturbances, and they found that a Carrington-scale event using the value of negative 850 nanotesla, they calculated that from 2012 to 2022, the probability was 12%, which is substantially higher than any sort of other Earth-altering event, such as an asteroid or comet impact, or such things. So, and obviously this is all based on several assumptions, like a power law dependence and what's called time stationarity of the data set. But basically using what was available at the time, this 12% is a rather unsettling value. Now, what's the estimated cost of such an event in this day and age? Well, it's been reported in the National Research Council report that such an event would take approximately 4 to 10 years to fully recover from, and could end up costing the US $1 to $2 trillion in the first year alone. And the reason for such a large value is considering the fact that if people don't have electricity, then a lot of people can't actually work in their jobs, let alone everything else that's very highly reliant on electricity, such as water and gas and infrastructure and these sorts of very vital utilities that we all very heavily depend on. In addition to that, the geostationary satellites, there's many of them up there now, and many commercial satellites up there now, and their combined revenue equates to about $25 billion per year, and it's it would be estimated that such an event would severely dent the capabilities of each of these, or all of these geostationary satellites, and this could end up costing $25 billion per year until they're replaced. And when you put these two figures next to some other major events that have taken place, like the Tohoku earthquake in Japan, which has been estimated at $200 billion thereabouts, Hurricane Katrina, about half of that. And also there was some significant flooding in northern Australia back in 2010, 2011, and that cost $5 to $6 billion. So, you know, on such a list, you can easily see that such an event would be among the most costly, if not the most costly event on record. And keeping in mind too that even if such an event were to be localized in its effects, like for example if it hit the US power grid, as we saw with the global financial crisis more recently, such effects do filter their way or do propagate their way all over the world, and so this would hurt many people financially, which is again rather unsettling notion. So to summarize and conclude, well, we started off by having a look at this event in 1841, where we first had a 16-minute train delay, and that seemed like quite a moderate effect of space weather on technology at the time. But as time's gone on, we've obviously developed technologies, and we're heavily relying on space-based technologies now that are much more vulnerable to this environment than what they were decades ago, even years ago. And so the importance of researching such such phenomena and better understanding their impact on us and our technologies is increasing with time. Given this 2012 event showed that a Carrington-scale event is still very much possible in this day and age, such event hitting Earth is really only a matter of time. So this is definitely an important area of research. And that's pretty much it from me. And I'd like to open up to any questions if you have them.
All right, let's give our speaker a round of applause. All right, so we're going to open it up to questions here, and we're also going to open it up to questions for anyone watching online. If you are on the Google+, we're going to use the Q&A feature, so that you can type in a question and Brett and I can see that. If you're on Twitter, use the hashtag #GHOSeminar, and I'll be monitoring that. And if Brett has his phone up, then he can take a look at that as well. So first off, do we have any questions here from our audience? All right.
So the earliest case, which was the 16-minute train delay, how exactly did it affect the train?
That's a good question. The telegraph infrastructure that was in place at the time is just for train signaling. So, as a train goes along the track, it needs to know whether or not the track is clear further up. And as the train approached one of the signals, it was flicking on and off, and it wasn't clear what exactly was going on. So for safety reasons, I assume the train stopped. I think I had somewhere in the presentation a quote from the superintendent at the station nearby. I think he was quoted as saying that someone kept on playing with the signals and wouldn't let them work properly. So that's so read into that what you like. Yeah, but that was pretty much it.
Okay,
that makes sense.
All right, Lucas.
So you were mentioning how basically these events are so catastrophic on today's technology, and how if we had another event, basically we're not going to have a whole lot that we can do with it. Is there some direction that we can head and some precautions that we can take to try and prevent losses or warning of such an event?
My understanding, there are many impacts of space weather as I've gone into, but the most serious one is the effect on power grids. And at least I'm aware of the power grid operators in the United States in particular. I think they've been taking this very seriously. Same with various places in Europe as well. So basically, the places on Earth that have been burned in the past, excusing the pun, obviously, these guys have taken this sort of thing more seriously, and what's so that's good. It's a very good thing, and I definitely don't want to be pointing any fingers at anyone for not doing enough. The problem is, as researchers, we have to argue importance of any particular research objective. So everyone uses these extreme events to try and motivate our research, motivate people to give us research funding. So we have to call on that. But the reality of it is these are relatively rare. And as I've said before, people have taken a lot of comfort in thinking, look, these extreme events, they're very rare. So it's like building like just recently, in the last few years, I think our state government in Australia, in Victoria, built a desalination plant to prepare for future droughts, because we'd had a decade-long drought or something like this. As soon as the desalination plant was constructed, the rains start again. So it's one of these things. How much money do you invest in it, and how what's the probability of such events? And because it's relatively low, it's difficult to know how much. I mean, we obviously can't throw everything we have at it, so we've got to be careful and realistic in how we actually argue for the funding. But there are, I don't know in particular what exactly power grids operators do. I do know that they monitor their grids in real time, and I think depending on where you are, they actually have to operate their power stations to meet demand as it changes. And the way geomagnetic activity affects their system is it looks like demand goes up or down, or supply goes up and down, and they've got to try and balance the equation somehow. And this actually ends up affecting the wholesale price of electricity between electricity grid operators themselves. So ultimately, this is potentially even an economic argument for even the smaller events that take place. But I think in terms of doing something about it, I think there are, I have heard of relatively simple and cheap and effective ways of dealing with overloading grids. You can replace power lines very, very easily. That's not a big issue. The bigger problem are the transformers themselves. And my understanding is that there aren't too many countries in the world that still manufacture these transformers. So if there was a global catastrophe, then we don't have the expertise all around the world to try and get our infrastructure back up to speed. So I think that's why they've got the 4 to 10 year buffer, and how long such an event would take to get all the infrastructure back in place. So I think to come back to your question, are we doing everything we should be? I think we are. So I'm not going to be alarmist and turn around and say, oh, we're all going to die, give me money. I'm being realistic and saying, we need to be careful with how our money's spent, and I think it's going to the most important areas. Because you can do without your GPS satellites for a couple of days as a person. Even cellular service. I know the younger generations are struggling a lot without having internet for tens of minutes, but they'll learn to live with it if it happens.
Well, to me, you would think that governments especially would be worried about that, because if you could knock out the world economy, that would be pretty significant, right? You could walk around and say, all right, well, if I don't have my GPS or I don't have my cell phone, well, that's a bummer, but I can still get by. But
yeah,
if your bank has shut down and your government can't work and everything is going crazy, that's really significant. Yeah.
Even going back to Hurricane Sandy, I remember seeing images of New Yorkers lined up for miles at gas stations because the electricity wasn't on to pump the gas. So people are having to hand pump the gas. On top of that, most of our money is all accessible via electronics or via ATMs and the internet and all this sort of stuff. So imagine if you don't have access to all your money, you don't have access to the infrastructure you had. If the supply of gas and water, fresh water to properties is reliant on electricity, which it is, you could easily see this escalate into a very serious issue. But to come back to the issue of, our governments, governments I think do take this sort of thing quite seriously, but I definitely think that some governments take it more seriously than others. But again, I think it comes back to, whoever's been burned in the past are the people that are, other countries that are really getting on board. Whereas, for example, Australia hasn't really had a catastrophe, a space weather-related catastrophe before. As you mentioned, as I mentioned earlier, the thing that happens most in Australia that gets reported is aurora sightings, and then they're quite often over top of Tasmania even though they may be affecting the power grids there, we're all relatively close and nearby, and so I think though a lot of it comes down to communication between us and government about the seriousness of such effects. So I think the US has been very good. The researchers in the US have been very good in getting involved with the research with government and making them aware of what's going on. And people in Australia, myself included, are always trying to do what we can to advise the people that need to know.
What would it be equivalent to, say, if you set off a nuclear bomb, right, and you had that electromagnetic pulse? And what's sort of the equivalent for some of these events that you've mentioned that were historically recorded and some of the damage that was done? Is it comparable at all?
I think in terms of an EMP, electromagnetic pulse, I guess that's what you're getting at. It's these magnetic field changes are generally a lot slower than EMPs, for example. So what you expect is not like an EMP, for example, will fry the circuitry inside of your actual PC, whereas the type of ground-induced, the geomagnetically induced currents that we're talking about, they tend to, they affect a very large region. And they create large potential differences that are separated by hundreds of kilometers. So if you've even got a small power grid network, the chances are your potential differences across that power network aren't going to be too substantial for you to worry about it. It's more the continent scale power grids like the United States, Australia, and much of Europe that's more of a bigger threat than the smaller scale stuff. So it happens over a large space. It happens more slowly. It's not like an instant like this. It does take several minutes. So, and this works for power grid operators because they could actually see something taking place in real time on their system and start to try and counter it. So an EMP and geomagnetically induced currents, or the magnetic fields associated with that, are very different, but mostly in their temporal and spatial scales. So, yeah.
Okay, so that makes a lot more sense. Yeah, the EMP is going to be a point source, where this is coming across continent-sized event. We've got a question on Twitter. Alexa Halford has a question. She says, "What's the smallest geomagnetic solar storm that causes effects on technology?" So this is sort of, okay, how small do I have to make a storm to see an effect?
Yeah, this is a loaded question.
Good.
Well, okay. What I'm going to bring this down to, basically, what she's getting at is our more recent findings that we actually don't need these huge solar events in order to have observable effects on the ground. We can actually have small blips that end up affecting various technologies in various ways. But I don't want to give too much away. We're on the cusp of we're currently working on something that's, along with Dr. Halford, trying to answer this question quantitatively. And our findings so far suggest that we actually don't need the big storms. We only need a small little perturbation in the solar wind, which may not even be due to any sort of explosion or anything on the solar surface. So, yeah, so we're finding that again, as I mentioned earlier, we're needing to be viewing space weather and space weather prediction much like we view normal weather prediction, as on a daily basis, on a day by day or hour by hour type basis. So just because of all the things that it affects and the amount of people that it affects. So that's the way I'm going to answer that question, Alexa. Thank you very much.
So basically, see our upcoming paper.
Yeah, that's right. Well, we'll let you know if it actually makes it. Yeah.
Cool. So we have another question here in the audience, Lucas.
So I might be a little bit confused here. You're saying that you can see these coming over a few minutes, and the power grid can adjust it. So if they have this space weather prediction, I mean, would it be obviously more beneficial if they just shut everything down for like a few more minutes and like let it black out for a few minutes rather than letting it explode and go on for a few hours, a few days?
Yeah. Yeah, look, it's tricky. The idea is to be giving people a bit of a heads up. I mean, okay, from a power grid operator perspective, which I'm not too personally familiar with, admittedly. The way I understand that this sort of thing would be useful to them is similar to, I guess, organizers of outdoor events are looking at the rain forecast. You know, they're like, okay, rain's likely, you know what, we'll start to put processes in place to deal with the rain, you know, by putting up tents or moving the festivities inside and all this sort of stuff. So the idea is that they know that something, you know, could be around the corner, that they just need to sort of keep an eye out for strange things. That's sort of the way I think, because space weather affects so many people in various different ways. I think a little bit of increased general knowledge about space weather and its impacts on these technologies is then therefore going to be a way for people to utilize these predictions in the future. Same deal with these rain forecasts. You check on your mobile app what the rain likelihood's going to be. You make that decision. You make the decision as to what to wear and what exactly you're going to do to suit your personal needs. Whereas other people that, you know, maybe from tropical climates, they don't mind getting rained on and they don't bother walking around with an umbrella and stuff like that. So it's really up to the person who, I guess, through increased you know, general knowledge and general awareness of the near-Earth space environment and how it actually does affect them, they're going to be able to make these decisions on this, you know, by themselves. I mean, things like sat-nav accuracy, as I mentioned before, these things are typically about 10 meters. You know, it will get to 10-meter accuracy, so they're not that fantastic. But agriculture, for example, these guys are starting to rely on precision GPS positioning, and this is centimeter level. And if they don't get it, then their machine, you know, a red light comes on and they're like, all right, it doesn't work. I'm going to go and have coffee until it fixes itself. Whereas if they've actually got the knowledge as to what physical phenomenon's caused it or is causing it, then they're going to know, okay, this is going to last for hours, so I'll take the rest of the day off, or this sort of thing only lasts 10 minutes. I'll just sit and wait it out. So it's really, again, much like weather prediction, the idea is to get the information out there enough so that people can make an educated decision about their particular and personal applications. And yeah, so that's essentially the way I see space weather prediction evolving to. I probably should plug in the space weather woman here, Tamitha Skov, over in the United States, that is on Twitter, and she's very active in tweeting all sorts of space weather prediction updates, covers all sorts of all sorts of technologies, including GPS and other types of technologies that are affected. And she does this, as I mentioned, like in a normal tropospheric weather style way, or weather prediction way, up in front of the screen and giving the presentation. And I think that's the future of this entire area of research, actually. So good on her. Check it out.
What was her name and what's her Twitter handle?
You know what? I could probably, I'll look that up real quick. Name's Tamitha. Well, she's got on here is Tamitha Skov, Tamitha, and the last name Skov for victory. So she's a space weather researcher as well. And I mean, I love her updates. I mean, I don't get time to watch all the satellite feeds and all this sort of stuff, but yeah, so it's great and very useful information.
Cool. We'll have to look her up. Awesome. All right.
Just out of curiosity, how did you get into researching space weather?
Sort of fell into it. I was always interested in space and particularly astronomy from quite an early age. But I guess definitely going through what we call primary school, so your equivalent to elementary, and then high school. My grades were not particularly fantastic, as my teachers will still attest to. But it wasn't until honestly my honors year, my undergraduate course, which was in space science, which is it was a very broad bachelor degree, but it was focused on mathematics and physics, which was obviously very helpful. But then during my honors year, I actually learned how to do exams. I learned how to study, and I learned how to perform well in tests, and ended up getting relatively good grades, and I went straight into a PhD at La Trobe under my then supervisor at the time, and I haven't looked back since. I think the more I've been getting into this field, the more excited I've been getting about it because of its applicability to people. Whereas everyone, I mean, lots of people, myself included, have always loved hearing about astronomy, you know, black holes, cosmology, dark matter, all this sort of stuff's fantastic. But I think it would surprise people to learn that we know very little about our near-Earth space environment. And the thing is, as technology is advancing, we're more and more vulnerable to what's going on. So we need to figure all this out. But that's pretty much in a nutshell my path, the way forward is very sort of straight and narrow. I didn't really sort of spend some time dabbling in something else. I just once I was accepted into my bachelor course at La Trobe in space science, I just kept propelling straight through, and yeah, straight through all the way to do the PhD. Yep.
Okay, cool. Well, since you're just recently out of your PhD, what advice might you have for these folks who are in their, you know, sophomore, junior, maybe some going into their senior year as undergraduate physics majors? What advice might you have for them?
Definitely, if you're looking to do research in academia, you need to be seriously considering postgraduate work. But try not to think about it in terms of, oh, geez, another, you know, however many years. PhDs in Australia they take 3 years, whereas in the States, you guys have classes on top of your normal research, and that ends up doubling the length of time you guys spending doing your postgraduate studies. You know, don't be daunted by this. Don't be sort of too drawn back, thinking, gee, there goes all my life. If you honestly are really loving the stuff you're doing, keep doing it, and it'll take you somewhere nice enough at the end of the day. I basically work forward with the idea that if I studied hard enough and got good enough grades, then I'd be somewhat financially rewarded later down the track. And, and that's relatively worked out well for me. Even though I definitely know that physicists aren't the best paid in the world, I probably could be making a killing in finance or economics or something like this. But you know, I've got something I like, I can get out of bed for each day, and I love it. And this morning I got up out of bed for you guys pretty early. So, yeah. So, yeah, that's pretty much the advice. Like, don't, you know, another, I guess, key bit of advice is don't, and you guys clearly aren't afraid of asking questions, and that's brilliant. I was one of these people that was quite timid and was worried about looking stupid in front of people. But now I'm not timid about that at all, and I'm quite happy to be ignorant about all sorts of stuff quite publicly. So I think it's a great attitude to have, and it's really a great way to learn. And especially going through postgraduate studies, and once you start presenting research on an international level, you'll get criticized, and you'll actually learn to love that. You'll learn that it's fantastic if people are actually shouting you down, saying, no, you've done this wrong, because then you're learning learning about what they're saying, and you should be taking that on board, not personally, but professionally. And then you can take what you learned from them to better yourself and to better your work later on. So, you know, be open to the criticism. Don't take the criticism personally, because it's not, unless they're saying that you're a terrible person, which never happens. But if they're telling you that your work's fundamentally flawed, hear them out, and feel free to disagree. But sometimes you do need to pull your head in and say, you know what, I think they've got a point, and and don't be scared of an evolving opinion about something. You're allowed to change your mind. Don't be scared of this, and this is probably something that the broader society could deal with, especially politicians. They're allowed to be wrong sometimes, we get away with it quite regularly, and we, I don't know how we're able to do that, but people still trust us, so that's good.
So what's your plan going forward? What are you going to do now?
Oh, geez. Well, I'm going to get another coffee after this finishes. At the moment, I think my personal goal at the moment, as it stands, is to try and do much of this sort of thing, raising awareness about this area of research, but focusing on Australia. There's a handful of academics in Australia. There's probably 10 to 20 of us in the country that are working on this, and we're all in very, very separate fields. Even Dr. Halford, her and I are close friends, and we interact quite a fair bit, but she studied something completely different to me, and it's quite a challenge for me to have an educated discussion with her about her research, because I don't know what she's talking about, and vice versa. and so these sorts of discussions are very very important. So we've got a diverse group in Australia, but we're looking to solidify and make the space physics group or space physics capability in this country better. But I mean, in such funding climates, it's challenging. But it looks like from various decades, and maybe Will, you can attest to this. Funding never is easy. It might have been back in the 40s and 50s. I don't know, but it's not anymore. So we've got to work for our cash.
Yeah, that's always the case.
Yeah, so that's what I'm hoping to do.
Okay, well, we really appreciate your time. Do we have any other questions here before we give our speaker one final round of applause? We're cool? All right. Well, thank you, Brent, very much. This has been fantastic.
Thank you guys.
I definitely want to thank you for your time. This has been great. Talking to us from the other side of the planet is very cool. I hope that we can do some more collaborations and seminars with folks in Australia, because you guys have been wonderful. So thank you a lot.
Great, no worries. I was very happy to. This has been great. Take care of yourselves and enjoy the rest of your night.
All right. You have a good Wednesday.
I'm going to go start work.
All right. Thanks. Bye-bye.
See you later, guys. Have a good one.
Bye-bye.